February the 19th, 1962, Lecture 22.
I'm continuing the last lecture for a few, I make one or two more points that I left out at the end. And that, of course, will squeeze this lecture and so on at infinitum. It's a very bad thing to do. It's like the budget that they planned. The questions that we were discussing were the various effects of angular momentum and rotation. And I mentioned some applications, but in addition, there's some very interesting problems in astronomy that have to do with angular momentum. One of the most striking characteristics of the solar system, well, it was first discovered that everything goes around in ellipses and so on, and that was understandable ultimately by the law of gravitation. But there are a whole lot of other simplifications of the solar system's peculiar things. Everything turns the same way. The moons that go around the planets, with few exceptions, turn around the same way, and so on. And it's an interesting question, of course, that has something to do with how the solar system got the way it is. And in studying how the solar system got the way it is, one of the most important considerations is the consideration of angular momentum. If you imagine a whole lot of dust or gas or something condensing, contracting as a result of gravitation, even if it has a small amount of motion, because those arms are coming in and the angular momentum is maintained constant. The moment of inertia is going down rapidly, the angular velocity has to increase. And it's possible that the planets are merely the result of this necessity, that it has to dump its angular momentum from time to time in order to be able to contract still further. We don't know. But it is true that 95% of the angular momentum in the solar system is in the planets, not in the sun. The sun spins, right? It's only got 5% of the total angular momentum. The problems of the origin of the solar system have been discussed many times, but it is still not analyzed. How does a gas or contract by slightly rotating, or how does a pile of dust fall together when it's rotating? Most considerations, they pay lip service at the beginning to the angular momentum, then when they make the analysis, they disregard it. It's pretty clear that it has something to do with it. Another serious problem in astronomy has to do with the development of the galaxies, the nebulae. What determines their form? On this particular slide, we have 4 or 5 nebulae. It's a specially selected part of the sky where you see 4 different types. Here's the famous type of ordinary spiral, much like our own. This is a special spiral which has long tails out here. This is a spiral, if you look at it right, it's sort of like a barred spiral, or a bar going out from here to here. And the ring that goes around it is not the same kind of trailing tails as it has in this case. And the question is, what is the difference from one to the other? How do they get different? What can the differences be? They could be, of course, that the masses are different. If you started with different amounts of mass, you come out with different conditions. That's not very likely. It's likely possible, but most likely, I certainly clear, that this spiral character has something to do with the angular momentum. So the condensation of the original masses of gas